Is this clear so far? We're told that the angle between the line and the plane is 30 degrees, right, which I have there, and that's the acute angle. Vector equation of the line is here, the plane's equation is here, and ultimately we have to figure out what the component P is. Okay, now the fact that we're given the angle between the line and the plane strongly suggests that we need to be coming up with an expression for the angle between the line and the plane. Hopefully we all agree with that. Now there's a key thing there, as far as angles are concerned, angles and vectors are concerned, I should say, is that we know that the angle between two vectors can be found using the fact that cosine, let's call that angle alpha, cosine of alpha is going to equal to, if I come up with two generic vectors u and v, u dot v, right, over the product of their magnitudes. So magnitude of u times the magnitude of v. In fact, let me make this clear. That's a multiplication. It's not a dot product at the bottom.
It's not cross.
No, it's not a cross product. And you know it's not a cross product because the magnitudes aren't vectors, right? They're scalars. I'll add to this, though, the u dot v, remember, the scalar product, it's perfectly possible for a scalar product to be negative. Therefore, to make sure that the angle alpha is an acute angle, what we do is we place this numerator inside an absolute value.
Why?
Because let's say I've got cosine of alpha equals to negative 0.5, then the only way that could occur, if you think of the unit circle, is if I'm dealing with like this type of angle, an obtuse angle. If I'm dealing with an acute angle, it means I'm in the first quadrant of the unit circle, and in the first quadrant of the unit circle, the angle has to be acute, of course, but cosine has to be positive. Does that make sense? So that's why I'm sort of forcing that absolute value there to make sure that I end up with the acute angle. So in this context, the two vectors that we're dealing with, let's sort of try and picture this. We've got the normal to the plane, and we have a direction vector for our line, which runs parallel to line L. I'll call that direction vector u. The direction vector in this case, just to hopefully be clear, is this vector here, the one multiplying the parameter, right? So if I write that on the side here, vector u has components 1, negative 2, p. Okay? Now on the side, what I strongly suggest you do, I'll show you exactly, I mean, maybe you can see it, I'm not sure, but like this is what I was doodling from home when I prepared for the lesson and stuff. I've got little doodles down here with literally vectors that I'm drawing. And this is what you should be doing in the exam. Don't stare at it, because you're not going to see it. It's a very visual topic. You need to draw things to see them. And so here's the type of thing that I drew. If I say that the vector normal looks like this, so I'll call that my vector n. Oops, vector n. I know, because of the inclination of the line, it's at 30 degrees to the plane, that the direction vector of the line looks something like this. So that, if I may do this for a second, you'll understand what I'm doing. Don't worry. Let me just adjust that, make this a dotted line. There we go. This angle here is the 30-degree angle. But based on that sketch alone, since the normal is perpendicular to the plane, and that angle 30 is measured from the plane, what's the angle between the two vectors? Exactly. So you now know that the angle between the two vectors is 60 degrees. Does that make sense? What that tells us is we can now use this formula with vectors u and the normal to the plane with cosine of 60. This is a paper one without a calculator. Cosine of 60 is particularly convenient. What's cosine of 60 degrees? 1 over 2, right? So here, at this stage, you'd say, all right, cosine of 60 is equal to the absolute value of u dot n over the product of the magnitudes of u.
Why did you change to n from v to n?
Because I don't have a vector v in this context. What I wrote in the upper right-hand corner is for any two generic vectors u and v.
Okay.
But in this exercise, the vectors that we're dealt, essentially, are the direction vector, which I decided to call u, and the normal to the plane, which I, as usual, called n, right? So hopefully you can appreciate that technically we have everything we could possibly need now. There's only one unknown in that entire equation there, and that's going to be p. So let me show you what I mean. u dot n, well, that's equal to the dot product of 3, my apologies, I misread. That's equal to the dot product of 1, negative 2, p, with the normal vector, which we said was 2, 1, 2.
What about mu? Does it not come into play at all?
Not at all. What does mu do? It stretches that vector u. It doesn't change its direction in any way, right? Or although it could change it into its opposite direction if mu is negative, but it's still going to run parallel to the line.
So you could use 2, negative 4, and 2p.
Absolutely. Yeah, and it would still work. So here, if I open up that scalar product or dot product, that's 2 minus 2, very convenient, plus 2p. Okay? So we quickly realize that dot product is just equal to 2p. Yeah? The magnitude of n, let's start with that one. Well, that's equal to 2 squared plus 1 squared, 1 squared plus 2 squared, all of which is under a square root. That's equal to square root of 9, which is very convenient again. That's equal to 3. The magnitude of the direction vector u, actually let me write that on the side here. Let me just move that over here. The magnitude of the direction vector u, well, that's going to be in terms of p, of course, but that's equal to the square of each of its components, or the sum of the squares of each of its components underneath a square root. In other words, that's equal to the square root of, where's u? 1, negative 2p, right? It's this one here, right? So that becomes 1 squared, which is just 1, plus negative 2 in parentheses squared, which is 4, plus p squared. And all that's under a square root. So that's equal to p squared plus 5 under the square root. There we go. Are we okay with that? We're good so far?
Yeah.
Okay.
Yeah, I did 5p squared. So then I did 5 times p squared, not 4.
Yeah. So here, if I replace, going back to my equation here, if I replace cosine of 60 by 1 over 2, the dot product I have inside this absolute value by 2p, and this denominator here by 3 times the square root of p squared plus 5, well, hopefully you can appreciate that that entire thing turns into this. It's 1 over 2, which equals to the absolute value of 2p over 3 times the square root of p squared plus 5. Rearranging all of that, so I'm trying to make it all fit on one single screen here. Rearranging all of that, that quickly turns into 3 times the square root of p squared plus 5. Careful, that looks a bit like a minus. That's not a minus. There we go. Under a square root, of course, which is equal to the absolute value of 2p. Don't avoid the absolute value, by the way. Every year in the IB exam, when I correct it,
Start with the half rule.
You're right. I made it disappear. It should be at the front. That should be a 2 there. Yeah, so I multiply both sides by 2, and I multiply both sides by the denominator that we have on the right-hand side.
We still need the absolute values?
Yeah. Keep it to the... I know we're tempted to get rid of it, but you're going to get rid of it in basically just a minute. You get rid of the absolute value when you square both sides of this thing.
Yeah.
Not before.
And you mark it.
Don't pretend, and please don't pretend it's not there, because every year when I correct IB exams, some students sort of, from one line to the next,
Yeah.
it just vanishes. And it's like hoping the examiner won't notice. We notice. It's obvious, right? It's really obvious. You get rid of that absolute value once you're in a position to say everything is now positive, no matter what. And everything will be positive here when I square both sides of this equation.
Yeah.
Does that make sense? So in other words,
Sorry, did you mark it down? If you saw they just got rid of the...
oh yeah.
Yeah.
At HL, very frequently, it's explicitly written in the mark scheme to knock a point off.
Wow.
SL, I'll be honest, not so much.
Okay.
HL, absolutely. Okay? So at this stage, sorry, I know I usually do my working vertically, but I want to make it, try and all fit on one single slide here. But at this stage, what we would do, I'd square both sides, right? So when we square the left-hand side, the 3 gets squared and the square root gets squared. So hopefully you can appreciate that that turns into 9 times, in parentheses, p squared plus 5. And on the right-hand side, both terms in that product get squared. So 2 squared times the absolute value of 2p squared. That's when you get rid of the absolute value. So technically, that's going to turn into 4 times 4p squared. Does that make sense? Because if you think of the logic behind that, this absolute value of 2p can either equal to 2p or it can equal to the opposite of 2p. So when I square it, either way, it's going to turn into 4p squared. Yeah, we're comfortable with that?
Yeah.
Good. This therefore turns into, carry on towards the right here, that's 9p squared plus 45, which equals to 16p squared. And hopefully you'll agree that's 45, which equals to 7p squared. In other words, and I'll write it in the center at the bottom here, p is going to equal to plus or minus the square root of 45 over 7. That should be your final answer. Done.
Okay.
Does that make sense? That's I like that exercise, by the way. Like there's a lot going on. And for what it's worth, the questions that you'll find in this worksheet, none of them are random. Like I chose these very carefully. Okay?
Good low.
They're good, yeah. These are good, proper IBHL math questions.
Do you have this on a PDF?
Yeah, of course. Yeah, and I'll happily upload it afterwards. So I got the PDF, and I can also download the mark scheme for you to see exactly how points are allocated.
Yes.
Okay, so I'll make sure to upload that as well. Okay?